This video demonstrates experiments with DCL-Sparse, a novel approach to range-based distributed cooperative localization. The S1 edge or the one-hop shadow edge method is a scalable method that utilizes inferred information to detect extra edges to add to the rigidity of the graph. For a dense setting with radius more than the GGR threshold, that is, when there is full connectivity, all the approaches and baseline methods converge to the ground truth, but DCL-Sparse converges faster. However, in the sparse conditions, there is not enough sensor data from the direct edges for the robots to converge. The power node approach may seem close to convergence in the beginning, but due to lack of rigidity in the graph, the robot estimates overlap. This phenomenon due to sparse connectivity is called flipping. When the estimates fall into a flipped configuration, the connectivity of the sensing graph exhibits a locally stable structure. However, this stability corresponds to a spurious equilibrium rather than convergence to the ground truth. Attaining the global minimum requires the system to escape this flipped state and resolve the associated non-rigidity. For instance, in the presented example, the robot formation flips along the 7-3 and the 7-0 axes. It results from the limited edge connectivity combined with unknown starting estimates. To overcome this, we use S1 edges, which are the inferred edges between a robot and its one-hop neighbor. These shadow edges strengthen the sensing graph, mitigating non-rigidity and promoting stable convergence even in sparse and noisy networks. This is the depiction of the real-world experiment, done on a 3 by 3 test bed for a team of 9 robots. Here we can see the ground truth on the left and the estimate frame on the right, represented by the real-world robot movements. The ground robots can only perceive their neighbors and the shadow edges from the one-hop neighbors. Using this information, our algorithm achieves localization stability. We validate DCL-Sparse through extensive simulations and real-world experiments, consistently outperforming state-of-the-art methods with up to 93% reduction in localization error and improved robustness in sparse graphs. Overall, DCL-Sparse enhances the accuracy, reliability, and scalability of multi-robot networks, providing a practical solution for large-scale, GPS-denied environments.